Okay, hello everybody. This is the last part of the Higher Physics 2019 written paper walkthrough. This is part 3 where we're going to look at questions 12 to 15. It's on the electricity stuff. That's internal resistance, capacitance and semiconductors. So, as usual, your data sheet may come in handy. Don't know if we're going to use it for the electricity stuff, but it's at the front of the paper if you need it. So let's dive right in where we left off. That was at question 12, and this is on internal resistance. So a student sets up a circuit as shown, and when switch S is open, the reading on the voltmeter is 1.5 volts. Then when the switch is now closed, the reading on the voltmeter goes down to 1.3 volts, and the reading on the ammeter is 0.88 amps. And in part 1, we have to state the EMF E of the cell. Well, the voltmeter is across the terminals of the battery or across the terminals of the cell, and it's measuring the terminal potential difference. And when the switch is open, the terminal potential difference is equal to the EMF. So that voltmeter reading of 1.5 is called the TPD, and the TPD is equal to the EMF when the battery is not doing any work, when no current flows. So for part 1, the EMF of the cell is 1.5 volts. And in part 2, we have to calculate the internal resistance of the cell. So we're going to need the voltmeter reading and the current when the switch is closed to do this. So when the switch was closed, the voltage went from 1.5 down to 1.3. So we have lost some of the volts inside the battery, and that lost volts will be equal to 1.5 minus 1.3. That's equal to 0.2 volts. And that's what we're going to use to work out the internal resistance of the cell. Using Ohm's law, R equals V over I. If we use the lost volts and divide that by the current passing through the cell, then we get the internal resistance of 0.23 ohms. In part 3, explain why the reading on the voltmeter decreases when the switch is closed. Well, when the switch is closed, there's a current in the circuit. That means the battery is doing some work. And when the battery is doing some work, some energy per coulomb is lost inside the battery. It's in the internal resistance of the cell, and we call that the lost volts. 12 part B, a battery of EMF 9 volts and internal resistance of 1.2 ohms is connected in series with a lamp, and the lamp's got a resistance of 2.4 ohms. And we've to determine the current in the lamp. Well, there's an easy way to do this, because that's just a series circuit. And really, from your National 5 knowledge, you could really do this just by using Ohm's law. The total resistance of the circuit is just the two resistors added together. 2.4 plus 1.2 is 3.6 ohms. And then we can work out the current in the circuit using Ohm's law. I equals V over R, as long as we use the supply voltage and the total resistance of the circuit. So 9 over 3.6. That gives us an answer of 2.5 amps. And remember, the current in a series circuit is the same at all points. So that's the current coming out the battery, that's the current through the internal resistance, that's the current through the lamp. Part 2, calculate the power dissipated in the lamp. Well, we have 3 relationships for electrical power on your relationship sheet. Which one are we going to use? Well, we know what the resistance of the lamp is, and we've just worked out the current through the lamp. So I'm going to use the power equation that's got current in it and resistance. So P equals I squared R. We're going to use the 2.5 that we've just worked out, 2.5 squared, times the resistance of the lamp was 2.4 ohms. And if you do that on your calculator, you get an answer of 15 watts. That's pretty straightforward. National 5. Okay, question 13. This is capacitors. A student investigates the charging of a capacitor, and the student sets up a circuit as shown using a 47 microfarad capacitor. The capacitor is initially uncharged, the switch is closed, and a laptop connected to an interface displays a graph of the current against time as the capacitor charges. So we've got a 47 microfarad capacitor, and part A says the variable voltage supply is set to 6 volts, and we have to calculate the maximum charge stored by the capacitor. Let's go straight to the relationship sheet then, and we're going to choose Q equals CV. That's the relationship that links charge, capacitance and voltage. We know it's a 47 microfarad capacitor, and the variable voltage supply was set at 6 volts. So C times V gives us the charge stored at that voltage of 2.8 times 10 to the minus 4 coulombs. Okay, part B, the graph shows how the current I varies with time as the capacitor charges. Then switch S is opened and the capacitor is discharged, and the resistor is now replaced with one that has a greater resistance. Switch S is again closed and the capacitor charges. Add a line to the graph above to show how the current now varies with time as the capacitor charges. Well, if we've got a greater resistance, we're going to have a smaller initial current, and it's going to take longer to charge up. So 2 marks there, one for having a smaller initial current and one for showing it's a longer time to charge fully. Okay, part C suggests an alteration the student could make to the circuit to increase the maximum energy stored by the capacitor. Well, remember it's a variable voltage supply, so increase the supply voltage. Okay, question 13D. Now, if you look carefully at the bottom here, this is the second one of the use your knowledge of physics questions. It's the open-ended question. And I suggest you leave this one to the end. It's about capacitors, but we'll come back to it at the end of this video. Okay, let's move on to 14. This is about semiconductors. Solids can be categorized as conductors, insulators or semiconductors depending on their ability to conduct electricity. Their electrical conductivity can be explained using band theory, and the diagrams show the valence and conduction bands of 3 solids, X, Y and Z. One of these represents a conductor, one represents an insulator, and one represents a semiconductor. And we have to complete the table below to show which is which. Now you should know that an insulator has got a large band gap between the valence and the conduction band. Semiconductors have a small gap between the 2 bands, and the valence band and the conduction band are overlapping in conductors, so that there's always free electrons in the conduction band. So, solid X is our insulator, solid Y with a small band gap must be our semiconductor, and solid X with the overlapping bands is our conductor. Okay, 14b, using band theory explain why conduction can take place in a semiconductor at room temperature. Well, remember the band gap is small, so electrons can be excited from the valence band into the conduction band by heat energy that's present in the room. And part C, silicon can be doped with arsenic to produce an N-type semiconductor. State the effect that doping has on the conductivity of silicon. Well, doping will make it conduct better. It will increase its conductivity, 1 mark. And then part D, resistivity is a measure of a material's property to oppose the flow of charge, and the resistivity of silicon is 2.3 times 10 to the 3 ohm meters. The resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. And we have to compare the resistivity of silicon to the resistivity of copper in terms of the orders of magnitude. Now remember, orders of magnitude is the powers of 10 in a number. So let's compare them for these two. We're going from 10 to the power of 3 down to 10 to the power of minus 8. So the resistivity of copper is 11 orders of magnitude smaller than the resistivity of silicon. Or you could have said it the other way, the resistivity of silicon is 11 orders of magnitude greater than copper. Alright, last question in the paper, and this is about the period and the length of a pendulum. Now, pendulum is not in the higher course, so this is a purely problem-solving question, and all the information that you need is in the question. So, a 1 metre long wooden rod has a series of small holes drilled at 10mm intervals along its length, and the rod is hung on a horizontal pin passing through a hole 50mm from one end. There's a diagram there showing you that. So, the rod is then raised through a small angle and released, and the period T is the time for the rod to travel from A to B and back to A. So, time for one swing, and we have to describe a method to obtain an accurate value for the period using only a stopwatch. Well, it would be very difficult to measure one swing accurately due to human reaction time, so what we should really do is measure the time for, say, 20 swings and divide the total time by 20 to get an accurate result for the period of the pendulum. 15b. The rod is hung from different holes in turn, and the distance h from the pin to the midpoint of the rod is recorded, and t is determined for each value of h, and the results are shown in the table. Part 1, we have to use the square ruled paper on page 41, draw a graph of t against h. Now, even if you don't know what's going on here, all we're being asked to do is draw a graph of t against h on your x-axis, t on your y-axis. And then we're going to need to use that graph to find out something else for part 2 of the question. So, let's look at this table. All the h values are decreasing, and your t values are decreasing, but then they increase again. So this is going to be a kind of strange looking graph. Also, your t values are very, very close together. It's got a very small range. And so do my h values. They're all kind of clustered together. So I am not going to start my graph from the origin on the x or the y-axis. I'm going to choose my axis quite carefully here. I'm going to copy that table down onto my graph paper so I can see what's going on. Now remember, we want height along the bottom. Label it first, height in meters. And my heights started at point 2, so I'm going to put point 2 at the origin of my graph and go up 0.25, 0.30, I'm going up in 0.05s, and I'm going up to 0.50, and that will cover the whole range of heights that I need. And similarly for the period values, all those period values are between 1.5 and 1.6. So I'm going to start my graph on the y-axis at 1.5 and then go up in 0.01s up to 1.6. So I'm going to go up 1.51, 1.52, 1.53, 4, 5, 1.56, 7, 8, 1.59 and 1.6. I don't need to go any higher than that, and don't forget to label it. That's the period in seconds. And then I'll plot my points. First point is when the height was 0.45, the period was 1.6. Okay, height 0.45, and then look up to 1.6, and there it's there. Then my next point is 0.4 and 1.56. 1.56 is there. 0.35 and 1.54. Okay. 0.3 and 1.53. 0.25 is also 1.53, and 0.22, blimey, that's a strange one. 0.22 is at 1.55. 0.22 is 4 boxes along. There we go. And the last one is 0.2, and that's up at 1.58 again. So there's my points. Strange looking graph this. It's obviously a curve. Let's zoom out and we have to join all these points up. Best fit curve. So, and you want to be going through as many of the points as you can. There we go. 3 marks. 1 for the labels and the units, 1 for the scales, and 1 for plotting the points and the line. Part 2. Using your graph, state the 2 values of h that produce a period of 1.57 seconds. Okay, let's go and have a look at the graph. 1.57 seconds. And yes, the line does cut 1.57 at those 2 points. And we have to say what the height is for each of them. Well, for the first one, it's about 0.205, I think. And the second one is about 0.42. In fact, I'm going to round that first one to 0.21. So there's my 2 values of h that produce a period of 1.57 seconds, 0.21 meters and 0.42 meters. Okay, part 3, part A. Using your graph, estimate the minimum period t. That's the lowest part of the graph then. Well, it's below 1.53, but it's above 1.52. It's about 1.527. 1.527. But I'm going to round that again. I'm going to round that to 1.53 because all my t values were 3 significant figures. So 1.53. Then suggest an improvement to the experimental procedure that would allow a more precise value for the minimum period to be determined. Well, more precise values for the period measurements, I suppose, would give us a more precise value of the minimum period. But I think what we'll go for is take more readings around the turning point in the graph, around the region where the graph dips to a minimum. Yeah, I think that'll do. It's a strange question. Anyway, is that it? Oh, keeps going. 15c. The quantities t and h are related by this relationship. T squared h equals 4 pi squared h squared over g plus c. I have never seen anything like this in my life, where g is the gravitational field strength and c is a constant. Using data from the table on page 40, calculate a value for c when h is 0.3 and a unit's not required. Okay, I know what g is, and we have to use values from the table on page 40 to try and find c when h is 0.3. Okay, when h is 0.3 on the table, then t is equal to 1.53. When h is 0.3. Now, if I know t and I know h and I know g, I can substitute all them in. Let's rewrite this relationship. There it is. And let's substitute all those values in. So I know t is 1.53, so let's square it. Multiply that by h, that's 0.3. That's going to be equal to 4 times pi squared times h again, that's 0.3 squared, all over 9.8 plus c. It's c we're looking for. We can tidy this up. Let's do the arithmetic on the left hand side of the equal sign. All of that stuff is equal to 0.7, and 4 pi squared times 0.3 squared over 9.8 is equal to 0.36 plus c. So c will be equal to 0.70 minus 0.36, and that is equal to 0.34. 0.34 what? I don't know, but we don't need a unit. That's the strangest question I've ever seen in a higher paper. Anyway, there's the 4 words we always love to see. End of question paper. Or is it? Don't forget, we missed out an open-ended question. I said leave it until the end. It's this one about capacitors. The use of analogies from everyday life can help improve the understanding of physics concepts, and vehicles using a car park can be taken as an analogy for the charging of a capacitor. Use your knowledge of physics to comment on this analogy. Well, this is my answer. Remember, it doesn't have to be excellent or complete, it just has to demonstrate a good knowledge of physics to get 3 marks. You'll get 2 if it's reasonable, 1 if it's limited, and nothing if there is no knowledge of physics demonstrated. So, here we go. When charging a capacitor, it may be initially empty, and then when connected to a DC power supply, charge will move onto the capacitor, and when you discharge a capacitor, charge will move off the capacitor through the same conducting path. This is similar to cars entering and exiting the car park. Cars are all different sizes though, whereas electrons are all the same size. Cars will fill up marked spaces, whereas charge will build up in a way where the electrons are all equally spaced, but they'll get closer together as it charges. Graphs of charging a capacitor look like this. There's what the voltage looks like, builds up to a maximum. There's what the current looks like as it's charging, decreases from a maximum down to 0. In a capacitor, the voltage increases quickly at first, and the current is initially high, it's at a maximum, and it decreases to 0 when a capacitor is fully charged, whereas the movement of cars in a car park is random. And the size of the car park is like the capacitance of the capacitor. Unlike a capacitor, when a car park is full, then it cannot hold any more cars. And remember, you can continue your answer. If you've got time at the end of the paper, continue it at the back of your answer booklet. Just make sure you label the question again. It was 13D and it was the capacitor's open-ended question. So let's keep going. When a capacitor is full at say 6 volts, then more charge can be pushed onto the plates of a capacitor by increasing the size of the supply voltage. The speed bump in the diagram of the car park is like a resistor in series with a capacitor, and it will restrict the speed of the cars that go into the car park, and that's like a series resistor that restricts the current when charging a capacitor. There you go then. Would that get me 3 marks? I don't know. What a strange last couple of questions there. Anyway, that's the 2019 paper, and hopefully that's been useful to some of you. Anyway, good luck with your exam this year. And don't forget to check out the other videos that cover the multiple choice papers from 2015 to 2019. See you in the next one.